The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay, good afternoon. So this week we talk about quantum gases, ultra-cold atomic gases, and sure, there are ideal Bose gases, ideal Fermi gases, but I will spend 1 or 2 minutes on each because that's exactly solvable, it's in all the textbooks, that's simple. Quantum gases become interesting because of interactions. And in my lecture today and in my last lecture, I want to introduce you to Bose gases and Fermi gases with interactions. And they both turn superfluid, and the superfluid properties are determined by the interactions between the atoms. So the purpose of those lectures is, number one, to acquaint you with important phenomena in cold gases, superfluidity in lattices, superfluidity in just in free gas, in a normal gas without lattice, and superfluidity of fermions. But at the same time, I also want to have sort of a theme for you how we deal with interactions. And that kind of theme is that how theoretically we reduce unsolvable Hamiltonians to Hamiltonians which can be solved. And you will see that actually appearing in different situations with, well, similarities, but important differences. So just to remind you, we started out with the interacting Bose gas. In a homogeneous system, we have a very general way to describe scattering. Two particles with initial momenta disappear and two particles with momenta appear. This is a scattering event. Now, this means we have products of 4 operators, which is very difficult to solve. And the Bogoliubov approximation, which we discussed on Monday, replaces the operator for the condensate, for the zero momentum state, with a Z number, saying that, well, N0 plus 1 is the same, a little bit waving your hands, but it's also, you can say, the macroscopic limit. When we have a photon field with many, many photons, we can use a Z number in our Hamiltonian to describe the electric field. So that's the same spirit. So maybe, I should emphasize it. This is for atoms, what you're used to do with photons for your whole life. Okay, with that, we have transformed the Hamiltonian into a bilinear expression. And so at the moment you have a bilinear expression, you do a Bogoliubov transformation, you simply diagonalize it by finding a new set of operators where the cross term between A and B, or between A of k and A of minus k, disappear, and then you have solved it. And this is what we arrived at the end of the last lecture. We have, with those approximations, we have diagonalized the Hamiltonian. Our Hamiltonian is now, you can say, a harmonic oscillator Hamiltonian, or you can say it has become a gas of non-interacting quasi-particles. Each of those operators creates a quasi-particle, and the quasi-particle energy is E of k. And I explained to you that, as expected, the quasi-particle energy is simply particles with momentum h bar k for high momenta, because a high excitation in a Bose condensate is a free particle. But a low-lying excitation is affected in a major way by all these interactions with the Bose-Einstein condensate, and that turns the quadratic dispersion relation into a linear one, or you can say that turns a free particle into a phonon or a sound wave. So that's my review of last class. Are there any questions before we go further? Colin.
So does this require low density and weak interactions, or one or the other?
We come a little bit later to that, but in the end, there is a small parameter. The small parameter will be NA cube, the gas parameter. N, the density, A cube, the scattering length. It's usually the dimensionless combination of the two, which decides whether we are in the weakly or strongly interacting limit. There is another assumption which we have made here, but it's related to that, as you will see in a few moments, that most of the atoms are in the condensate. We assumed N0 is peak. The condensate depletion, the number of atoms who are not in the condensate at T equals 0 is small. But let me just first show you, I want to mix in theory and experiment, how sound can be observed. I should actually say this experiment is sort of dear to my heart because at some point it clicked to me how the new world of atomic physics connects with condensed matter physics. Soon after we had realized Bose-Einstein condensates, a famous condensed matter theorist said, hey Wolfgang, you should now observe sound. Sound is important. Yeah, okay. But how do you observe sound? You know, use a piezo and just kick the system and create a sound wave. And I said, oh gosh, this guy doesn't know that if we put anything in contact with the quantum gases, a piezo, the gases will just stick to it. He has no idea what our system is. But then I said, wait a moment, we have to translate. He says, use a piezo. Well, I have to translate in atomic physics, how do we kick atoms? With a laser beam. And in that moment, I had the idea that we can take a Bose-Einstein condensate, suddenly switch on a Bloody-tuned repulsive laser beam. This will do exactly as a piezo, create a density perturbation, and then the density perturbation will propagate with the speed of sound. And that worked. That was just when Bose-Einstein condensations were very fresh. One of the first scientific experiments done, we switch on the laser and you see color-coded in red the density perturbation which propagates outward. And the slope of this line is the speed of sound, and here we determined the speed of sound as a function of density. So that's how phonons can, or at least how the speed of sound and wave packets which propagate with the speed of sound can be prepared. I come back to phonons and collective excitations in a few moments. But let me first say, when we have diagonalized the Hamiltonian, we know everything we want to know. I just focused on the quasi-particle energies, but you also know the ground state energy. And actually here, Colin, you see that the corrections to the ground state energy scale with NA cubed. So this is really the small parameter in the system. But we can also find out what is the ground state wave function. And let me use that to introduce an important concept to you called the quantum depletion. When you have two atoms in the condensate at zero momentum and you switch on the interactions, the atoms, the interaction, the delta function interaction couples zero momentum state to higher momentum states. So therefore, the effect of interactions is that the condensate is not just at zero momentum, it has some probability or some admixture of finite momentum states. This is the ground state. This is how the Hamiltonian is diagonalized. So from the Bogoliubov approximation, where we introduce this V and U parameter to transfer from one set of Bose operators to another set of Bose operators, those coefficients give us the population of those momentum states in the ground state of the condensate. So if I now ask, what is the condensate fraction, what is the number of atoms in the zero momentum states, it's all atoms but those who have finite momentum. And we find again the small parameter NA cube. Now, this quantum depletion allows me now to make a distinction between the cold atomic gas condensates and superfluid helium-4. In cold atomic gas condensates, this correction is about 1%. So therefore, I can say with 99% probability or with 99% weight, the condensate, the many-body wave function of the condensate is just the zero momentum state to the power n. And this very complicated admixture of correlations into the ideal gas wave function is only 1% for alkali gases. But for liquid helium, the condensate fraction, even at zero temperature, is only 10%. So when people use neutron scattering, it would be a long story in itself how this is done, but when they use neutron scattering to analyze liquid helium at low temperature and figure out what is the fraction of atoms which have zero momentum, they found 10%. The quantum depletion is 90%. But that's just the difference between a quantum gas and a quantum liquid. And in the quantum liquid, in liquid helium, NA cube is on the order of unity. Okay, I mentioned this dispersion relation. These are sort of quasi-particles, and I at least showed you how you can measure the slope of the quasi-particle dispersion relation by propagating sound waves. But let me now tell you how we can observe quasi-particles, elementary excitations directly. And this is actually simply done by light scattering. If you scatter a photon, and the scattered photon loses energy h bar nu, and it is scattered at an angle, therefore it transfers momentum q. This process can only happen if there is an elementary excitation with momentum q and energy h nu. So in other words, on a photon basis, you can say photon by photon. If you scatter a photon, the photon transfers momentum and energy. The process can only happen if you can form a quasi-particle with this momentum and energy. So since this is sort of the direct way of mapping out whether the system has the possibility to absorb momentum q and energy h nu, this has sort of a name. The scattering probability is called the dynamic structure factor, and the dynamic structure factor is just an integral over all the possibilities that a many-body system can absorb momentum and energy. Now, there is one nice feature which was introduced by us here at MIT, and that is if you want to measure the dynamic structure factor, often you do it with neutron scattering. You scatter neutrons or X-rays, and they scatter spontaneously at an angle, and you need a detector to detect the scattered particles. But in our case, because the gas is so dilute, the distance between atoms is on the order of the optical wavelengths. We don't want neutrons, we don't want X-rays, we want photons, because the wavelengths of photons is perfectly matched to the properties to momentum transfer and such we need for our system. But photons, we have photon lasers. So instead of in a painstaking way analyzing the frequency and the momentum of scattered photons, we don't do the spontaneous scattering process, we do a stimulated process. We use two laser beams and we stimulate a photon to be scattered into the other laser beam. And by having the two laser beams at frequency difference delta omega, we are really asking the system, are you ready to absorb delta omega energy? If yes, then you have a quasi-particle. So this is how we do quasi-particle spectroscopy. And a few years later, this method was refined by the group at the Weizmann Institute. And what you see here is they varied the angles between the two laser beams, realized different momentum transfer. And what you see is the low dispersion, the linear dispersion relation for low momenta, and then the quadratic part at high momenta. So this is called Bragg spectroscopy. It's a variant, you can say, of Raman spectroscopy, where you go from a 0 quasi-particle state to a 1 quasi-particle state through a stimulated Raman process. And this is how the dispersion relation is determined. Okay. So I've so far dealt with aspects of a homogeneous Bose-Einstein condensate, where, of course, if you have a homogeneous system, you formulate everything in momentum space. But now we want to deal with the situation that our condensates are finite in size, and in addition, they are usually in a harmonic oscillator potential, and therefore their density is inhomogeneous. Let me start the discussion with the inhomogeneous Bose-Einstein condensate by showing again a picture which brings in some memories of 1996. It was the first time that we could see a Bose-Einstein condensate in the trap. Before, people have just seen it by time of flight when it was pretty much already destroyed or it was just flying out. But here we see the trapped Bose-Einstein condensate, and we could even take multiple pictures of the same condensate. So you can say this was the first time that a condensate was seen alive. What you see here is actually the bimodal distribution. You see the condensate, and then due to speckle pattern, the thermal cloud looks fragmented, but this is just a speckle pattern due to the signal to noise. But here you really see now, not in ballistic expansion as I've shown you on Monday, but really in situ the size and shape of the condensate. Okay, how do we describe it? Well, the message is pretty much exactly the same way as we did with the Bogoliubov approximation and such, but instead of in momentum space, we do it now in position space. Actually, I have to say this week I go through a lot of material, but what I'm trying is to give you sort of a spirited and animated overview that you really know what is important. Where is the same concept appearing again in a different way? The details, I've posted actually the original articles, references, summer school notes, some of them written by myself on the website. So yes, it's a little bit different character than other lectures. I want to show you a lot of things and put a special emphasis on the ideas. Okay, so in second quantization, we are now using field operators which create and annihilate particles at position R. This is sort of the single particle Hamiltonian, kinetic energy and potential energy. And our interaction term has now again 4 operators, 2 annihilation operators, 2 creation operators, but they are now formulated in position space. We do exactly the same as we did in the homogeneous gas. We assume the potential is short range. That means delta function, and that means we can get rid of one of the integrations in R and R prime. But we still have product of 4 operators. We can formally solve the equation by writing down Heisenberg's equation for the motion, for the equation of motion for those field operators, but of course this cannot be solved. Remember, products of 4 operators are hard. We have to reduce it to 2 operators. And this is actually done by the Bogoliubov approximation again, but it's done here in the following way. Remember, in momentum space, we replaced A0 and A0 dagger by the square root of A0. What we do here is we say this is sort of a quantum field, and when we have a superfluid, this field operator has an average value. It's actually the macroscopic superfluid order parameter. So we replace the operator by an average value, which we assume is large because many, many particles are in the superfluid state. And then we have fluctuations which are small. And what we will do is, well, it's pretty clear, when it comes to the fluctuations, we will neglect higher products of 4 fluctuation operators, and we are down to C numbers, and as you will see, 2 operators. We can, and this is even more dramatic, it wouldn't make sense in momentum space, but it does make sense in position space. We can even do a first approximation where we completely neglect those fluctuations. And then what we have is, when we simply insert a C number into, let me just go back, into this Hamiltonian, we have then an equation for this number, for this function psi, and this is the nonlinear Schrödinger equation, also called Gross-Pitayevsky equation, which is now the analogy to Schrödinger's equation, but now for the macroscopic wave function, which is occupied by many, many particles. And in addition to the kinetic energy and the trapping potential, the external potential, it has a term which is proportional to the density, and this is just a mean field repulsion which one atom feels exerted by the other atoms. I should say, so just to connect it to what I've said earlier about the quantum depletion, you can regard the function psi as the best approximation to an ideal Bose-Einstein condensate. So if you want to write your many-body wave function as a function psi to the power n, all particles are in the same quantum state, then a variational calculation would say that this function psi should obey this equation. If you want to read up what I've said, I've posted a recent paper from which I found very pedagogical, where they say where they derive the Gross-Pitayevsky equation without even using an operator, psi-Dagger, without using any second quantization. They just say we have an Hamiltonian for an interacting system, and we try to write the complicated many-body wave function as a wave function to the power n. And then you put this ansatz into your Hamiltonian and do a variational optimization, which single particle wave function psi, if taken to the power n, minimizes the total energy of n particles, including interactions. And the answer is this equation. So there are many ways. This equation is sort of very natural. Now, let's just, I mean, you all know about single particle physics, kinetic energy and an external potential. Let's now learn what this density-dependent term does. Well, it's pretty clear. There is a price to be paid for density. And well, the total integrated density is, of course, given by the total number of particles. That means if you lower the density somewhere, you have to increase the density. But because this is a nonlinear term, if you have an average density and you lower it here and increase it here, you have actually more repulsive energy than if the density is flat. So this term has only one goal. It wants to flatten out densities. So therefore, if we have a box potential, and you know the ground state in a box is just half a period of a sine function, if you now put in strong this is a non-interacting condensate. This would be the macroscopic wave function in a box potential. But if you now put in strong interactions, the strong interactions want to flatten out the potential. They flatten out the potential, and only at the very last moment, all right, now it's time to go down because we have to meet our boundary condition. And the length scale where you eventually go down, it has a famous name, the healing length, is the length scale where the kinetic energy due to the curvature of the wave function is now comparable to the interaction energy. If the system would curve down earlier, it would cost too much repulsive energy because the density is not kept flat. If it would curve down too late, the enormous curvature would mean a lot of kinetic energy, and this is just the best compromise between those two criteria. So that's how you derive the healing length. The healing length is now the length scale over which the system is willing to meet boundary conditions and not stay flat as possible. Timo?
Curious, in that equation, the m is the mass of each individual.
The mass is the mass of a single atom.
A single atom. It's not. I don't. Sorry, I wasn't here last class, but the quasi-particles have the same mass, or whatever it is.
In the Bose-Einstein condensate, they are.
Okay.
We haven't changed the mass. But we are not talking actually about quasi-particle. We are really talking about here qualitative features of the solution of the Gross-Pitayevsky equation. And the Gross-Pitayevsky equation is sort of a single particle equation for particles of mass, of the original bare mass m. It's a macroscopic wave function, but I sometimes say it describes the wave function of a single particle where all the other particles are included at the mean field level. So therefore, it is really the atomic mass, and not any form of collective mass here. Well, if you would now ask, how do interactions transform the first excited state in the box potential? Well, then it's again flat as much as possible. But then, if you want to maintain the parity of the wave function, then it's only close to the zero crossing within a healing length that the system says, okay, now I change sign. So that's sort of what is inside the Gross-Pitayevsky equation. Now, once we realize that, we can take it to the next level and say, well, if we neglect, let's say we are interested in the ground state, and we neglect this boundary region where the kinetic energy becomes important, maybe we can simplify the Gross-Pitayevsky equation by neglecting the kinetic energy. If potential energy dominates by far, we can neglect that, and then we should get a good description which will not be valid in the wings of the wave function, but in most of space. But now, if you look at this equation, it's no longer a differential equation. It has no derivatives. It's just something which applies, to the wave function psi itself, and we can simply solve that by the solution of that is that psi square, the density, is nothing else than there is a constant minus the inverted trapping potential. So therefore, in this Thomas Fermi approximation, where we neglect the kinetic energy completely, you just take your trapping potential, turn it upside down, and then you fill it up with density until you have accommodated the number of atoms you want to accommodate. And this is, of course, the constraint in the number of atoms is determined by the chemical potential. Or if you have a more complicated W-shaped potential, the same construction, flip it over, fill it up, gives you the condensate wave function, the density distribution of the condensate in this potential. I don't want to belabor it, but coming back to the question of the small parameter, if you look at those equations, you can identify a parameter which is, this is now the small parameter, or the parameter in the system which is the important dimensionless parameter. It depends on the number of atoms, and it depends now on the ratio of the scattering lengths, which characterizes the interaction, and the harmonic oscillator length. You can say the harmonic oscillator length is the ideal wave function harmonic oscillator, so this parameterizes the importance of kinetic energy, whereas the scattering length parameterizes the importance of interactions. And all those solutions can be nicely written as what you would have in an ideal gas, and then this parameter x. So in typical experiments, n is a million. The scattering length is smaller than the oscillator length, but n is a million, and this parameter x is usually large. So therefore, and I'm simply just talking about this solution, we have the situation that the chemical potential is larger by a power of x than the ideal gas solution, which would just be the ground state, the ground state with its 0-point energy in the harmonic oscillator potential. Or the width, the size of the wave function is larger than the ground state of the harmonic oscillator, but only with an exponent which is 1/5. Well, we can see that. These are now, again, somewhat improved pictures of condensates inside the trap. For the expert, the previous picture was dark ground imaging. This is now phase contrast imaging. And if we take a profile, we clearly see the condensate wave function, and we see the thermal wings. When we look at the size of the condensate wave function, you realize what I just meant, that the ground state wave function, the harmonic oscillator length, is 7 micron in the axial direction, but here we have 300 micron. So this condensate is completely dominated by interactions. And it fulfills very nice, and pretty much the whole shape, except maybe some details in the wings, are quantitatively described by the simple approximation I have explained to you. So just a little bit show and tell. We have this Gross-Pitajewski equation. The Gross-Pitajewski equation has, as Schrödinger's equation, a time-independent form to get the ground state. It has also a time-dependent form. You simply replace the energy by the derivative of the wave function. This is the time-dependent form. Everything is very simple, and you can do many-body physics, but on your computer you pretty much look for single-particle wave function and take them to the power n. So some areas where the Gross-Pitajewski equation has quantitatively explained experiments. One is the expansion of a Bose-Einstein condensate. It's this famous situation when you have an elongated condensate and let it expand. It expands faster in the radial direction. One simple argument is the pressure of the mean field is larger and leads to a faster acceleration. So therefore, if you have a cigar-shaped condensate and release it, it turns into a disk. it inverts the aspect ratio going from a cigar shape to a disc shape. And that has been beautifully and quantitatively described by the Gross-Pitajewski equation. Here we have measured the interaction energy as a number of condensed atoms. And I mentioned to you that this X parameter comes often with powers 1/5 and 2/5. And this here is a fit to the power 2/5, beautifully confirming the theory. So the Gross-Pitajewski equation was invented in 1962, about 50 years ago, by Gross and Pitajewski to describe vortices. Actually, Lev Pitajewski is still alive, going strong, and publishing papers. One of his latest predictions was solitons in Fermi gases, and I know in Professor Zwirlein's group, one of his lab just looked at the same physics and compared to the theory of Lev Pitajewski. And this year we are celebrating, I forgot, the 85th or 90th birthday of him. Pardon? 90? I know there's a poster next to my door, but I forgot which anniversary. So, I mean, he's a legend, but he's still walking, he's still doing science. So if you meet him, you go back to 50 years in history. Anyway, it is this Lev Pitajewski, and he invented his equations to describe vortices. So anyway, so we have this nonlinear Schrödinger equation. Let me just show you what vortices are and how they are formed. Vortices come if you solve the Gross-Pitajewski equation, or if you have ever any quantum fluid or quantum gas, and you add angular momentum. The angular momentum cannot lead to rigid body rotation. This would violate the fact that the velocity field has to be irrotational to make sure that the phase of the wave function is well defined. So if you rotate the system, it can absorb angular momentum only by forming vortices. And vortices are singular points of the wave function. Singular points where the density is zero. In other words, I don't have time to give to be exhaustive here, but when something rotates, there is a dynamic phase, you can say, because there are meta waves going in circles. And the integral of the phase has to be an integer number of 2 pi's. Otherwise, you would not have a well-defined phase of the wave function. And if you now say you make a circle which is 2 pi, you make the circle smaller, smaller, smaller. In the middle of the circle, you go around, the wave function changes by 2 pi, but what should the wave function do on one point? Which number between 0 and 2 pi should the wave function pick? Well, the wave function says, I can't pick, I just go to 0, and a 0 value has no phase, and I'm fine. That's exactly what the wave function tells you. So therefore, if you want to describe vortices, you want to now describe the Gross-Pitajewski equation, but with the boundary condition that the wave function goes to 0, and if you want to describe one vortex, you want the wave function to go 0 in the center of the cloud. And so you make a corresponding ansatz, you allow the phase to wrap around by 2 pi when the angle phi is varied, and then when you solve it, you have of course put in that there should be a 0 of the density at the center. And it's now nice for me there's an important review paper which describes all that and more, but it's nice to show you now the 2 extreme cases of the ideal condensate without interaction and the strongly interacting condensate. The ideal condensate, well, we are in the first excited state of the harmonic oscillator potential, and this is the dashed line, and of course the size of the hole, the 0, is pretty much on the order of the oscillator length because there is no other length scale in an ideal harmonic oscillator. But if you have the interacting system, remember what interactions are doing. They want to keep the density as constant as possible. Well, we are not in a box potential, we are in an inverted parabola potential. And remember, our Thomas Fermi solution, which neglects kinetic energy, is the inverted parabola up to here. And then the tail is when we can no longer neglect the kinetic energy. But if we now say, okay, fine, but now in addition, we want the vortex in the center, the wave function out there says no. We do what minimizes kinetic energy and what minimizes repulsive energy. We follow the inverted parabola, and only at the very last moment, on the scale of the healing lengths, the system meets the required boundary condition that the density goes to 0. Anyway, with this qualitative understanding, you can get a lot out of those. You can immediately understand the salient feature of this solution. Timo?
I know we're not talking in details, but is there a simple, maybe intuitive reason why when you spin a Bose-Einstein condensate, you get many vortices, but when you spin like your coffee in your cup, you just get one big one?
Yes. Okay. So the question is, if I have a wraparound of 4 pi in phase, whether the system should have a doubly charged vortex or 2 singly charged vortices. What is the difference in energy? Well, what happens is doubly charged vortices are unstable. My group at some point were the first to create doubly charged vortices, but we saw that they immediately decayed. Pardon? Initially, we couldn't observe. We just saw that it was unstable. But it's a decay into 2 vortices. But it's easy to understand. If you put 2 vortices on top of each other, what is the energy of the system compared to 1 vortex? Well, the energy of a vortex is the rotational field around it, and if you superimpose 2 vortices, the velocity around the doubly charged vortices is twice the velocity of 1 vortex, and therefore the kinetic energy is 4 times. If you have 2 vortices which are far separated, that it has its own velocity field, it has its own velocity field here, and when the 2 velocity fields come together, the velocity is already so low that you don't have to consider that, then those 2 vortices have an energy which is 2 times the energy of a single vortex. So and therefore, when the 2 vortices, they start out with 4 times the energy of a single vortex, and when they dissociate and repel each other, they have shedded half of the energy. So this argument tells you immediately that vortices are in effect repulsive, and therefore any multiple charged vortex will spontaneously decay. It's also this net repulsion between vortices which makes the vortices arrange in a regular lattice. The regular lattice which you saw before is nature's answer to how can we minimize the energy of all those vortices. And the idea is let's keep the average distance between them as large as possible. And the answer is a hexagonal lattice. Matt?
So a few slides back, you plotted we arrived at the GP equation, and you plotted sort of like in a box potential, the ground state, the first excited state, sort of comparing the GP equation to the typical single particle solution. And so I guess I'm a little bit confused about how sort of like excitations manifest themselves in the system. Because in some sense, like if you were to solve the GP equation, then would you arrive at say like a spectrum of solutions? And I guess I'd be confused whether the excitations manifest themselves into that spectrum of solutions, or rather than they become excitations like sort of deviations from the mean field, as including the extra current.
Matt, you're now asking about something more complicated. You're asking what are the excited states of the many-body system. And actually, we have already found one answer, and this is if you want this small excitations, it's one particle becomes a phonon or one particle becomes a quasi-particle. What we are talking about here is what happens if the whole macroscopic wave function is in an excited state. So we are asking here in the box potential, what happens if we force all n atoms to have one node in their wave function? And this is what I'm talking about here. So the excitation energy of this state here is much, much higher than of single quasi-particle excitations. I'm not sure if I'm addressing your question here, but...
So would single quasi-particle excitations, are those essentially sort of deviations from the mean field? Yeah, because,
No, they are, you really look for many-body physics, mean field deviations. Probably what you do is in that sense, yes, you're allowing in this ansatz that psi operator is psi average plus fluctuations. You now look for fluctuations and you're looking for the energy eigenspectrum of those fluctuations. And the answer are quasi-particles. So it is actually the Bogoliubov solution for the spectrum of the fluctuations. And the answer is the dispersion relation I presented to you. Whereas here we are asking what are excited states of the macroscopic wave function. It's a very, very different question which we have addressed here. Colin.
So when you stir the condensate, do you view it as, do you stir sort of at the trap frequency? So I do sort of n single excitations, or do you stir at n times the trap frequencies? You do one sort of n particle excitation.
Well, the experimental answer is you want to stir at the quadrupole frequency, which is square root 2 times the trap frequency. Then you create quadrupolar excitations. The quadrupolar excitation can be regarded as a standing sound wave, but you create a macroscopic number of those excitations. So you make actually the whole condensate wave function oscillate in a quadrupolar pattern, but it's a rotating quadrupole, and that eventually then rearranges itself and leads to vortices. So I think the correct answer is the most efficient way to create vortices would be to excite quasi-particles, but then excite so many, and this may relate to Matt's question, create so many quasi-particles that you have really a time-dependent and oscillating macroscopic wave function. So eventually you have a coherent excitation of quasi-particles, and that eventually means the condensate moves in a quadrupolar pattern, but it's a quadrupolar pattern with rotation, and that eventually turns into many vortices. But that's a really very rich question which you're asking, which has been studied in a lot of different aspects of that have been studied. Okay, so we've talked about Bose-Einstein condensates in an homogeneous system, just sort of to lay the groundwork. We've talked about Bose-Einstein condensates in traps in an inhomogeneous system. Now we want to talk about Bose-Einstein condensates in optical lattices. Well, there are two reasons why we want to do that. One is we want to use the Bose-Einstein condensate to obtain deeper insight into the properties of matter. And a lot of forms of matter appear in periodic lattices. So if we put a Bose-Einstein condensate into periodic potential, we can at least understand some of the properties of crystalline matter or electrons, which are Bloch waves in a periodic potential. So this is one reason why. The other reason why we want to go to optical lattices is the following. Ideal Bose-Einstein condensates are trivial. Weakly interacting Bose-Einstein condensates are entertaining, and you can write a lot of papers, have a lot of fun of it, develop your methods. Also mildly intellectually interesting, because how those weak interactions manifest itself in vortices and all that is really rich and interesting. But the conceptual problems appear when you go to strong interactions. Strongly correlated matter is where mean field descriptions no longer work. This is really the frontier of our understanding of many-body system. And when you want to be there, you want to create a strongly correlated system, and strongly correlated systems means that the interaction energy dominates over kinetic energy. In Bose-Einstein condensates, you can only go so far with increasing interactions via Feshbach resonances, because you get into some inelastic collisions. So that's one knob to turn. You go to larger and larger scattering lengths and crank up the interactions. But if atoms strongly interact, they start to do bad chemistry, they start to spin flip, they do other things, and in some cases you keep it under control, in others you just can't keep it under control. But another way to get to strong interactions means you reduce the kinetic energy. It's the ratio of the two which matters. And when you put particles in a lattice, well, the lattice actually reduces the kinetic energy. You may know from condensed matter physics that in a lattice there is an effective mass which is higher than the bare mass. Therefore, you have reduced the kinetic energy. Or if you want another hand-waving approximation, the kinetic energy is given by the bandwidths. And if the tunneling becomes slower and slower, the width of your band becomes narrower, and your kinetic energy is less. So anyway, I can give you many hand-waving approximations why in a lattice kinetic energy is reduced. And repulsive energy is probably enhanced because instead of having your atoms spread out, they are bunched up at each lattice site into a higher density cloud. So anyway, maybe you're interested in periodic potentials or you're interested in quantum systems with strong correlations. For whatever reasons, you want optical lattices. Now, I have here a few slides which introduce periodic potentials, but it is really just the single particle physics in a periodic potential. It has nothing to do with quantum gases. This could be the first lecture of how to describe electrons in a matter. So let me just quickly go through, assuming that almost all of you are familiar. But I use those slides also just to give you a few definitions and introduce a few symbols. So this is simple, boring, exactly understood physics. We have a Hamiltonian, which has kinetic energy, and a periodic potential, which is our lattice potential. It's rather trivial to solve that exactly. For your wave function, you use Bloch's theorem and write it by an exponential factor with quasi-momentum times a periodic function. And if you now solve Schrödinger's equation, you want to you use Fourier space, you Fourier analyze the wave function, you Fourier analyze the potential, and since the potential is periodic, sine square potential has only 3 Fourier components at 0, plus, minus 1 times the periodicity of the lattice. You do a Fourier expansion for your periodic wave function. And if you insert that into Schrödinger's equation, well, the Fourier transform has turned the differential equation into an algebraic equation because the second derivative simply becomes now k square or q square. So in other words, you have a set of linear equations. There is an index which is the band index. How high do you want to go? And usually you truncate it, but it's the same. It's really the same trivial story which is told in all textbooks of condensed matter physics. If you have no band structure, well, you have the parabola, but to prepare for band structure, I've broken it down here in the first Brillouin zone. And if you now introduce a lattice, you introduce band gaps, and you go from the left to the middle to the right for stronger and stronger lattices. So the case which I will be focused on, because it is the most extreme case away from free space, is this case which is called the tight binding limit, where the potential energy of the lattice is large, and large means compared with the kinetic energy at the Brillouin zone, which is k square. K is the lattice momentum, k square over 2m, and that's the recoil energy. So our dimensionless parameter here is the depth of the lattice measured in recoil energies of the photon, because that is the kinetic energy of the free gas at the Brillouin zone. Okay, there are a few things which immediately simplify that. Once we are in the tight binding limit, our lattice is really deep, and each side forms an harmonic oscillator, and the harmonic oscillator frequency is analytically given by the depth of the lattice. And the solution here for the lowest band is that the lowest band, the energy in the lowest band, the dispersion relation is, well, we have a harmonic oscillator at each side in x, y, z, so the average energy in the lowest band is the 0-point energy in x, y, and z, 3/2 h bar omega naught. And then we have a cosinusoidal band structure where q is the quasi-momentum. And what appears here as the only interesting parameter is j, and j is, I think this 4 should be 4j is the bandwidth. So what appears here now for the first time is j. It appears here as the bandwidth. But let me immediately give it another interpretation as a tunneling matrix element in the following way. Right now we have formulated the physics in Bloch wave functions, which are infinitely extended. The Bloch wave functions are for the lattice what plane waves are for free space. But if we have tight binding limit, there is another limit which is important, namely a particle is localized and hops around in the lattice. The localized particle, of course, is in free space. It would be a wave packet, a superposition of plane waves. So let's do the same in the lattice. Let's construct superpositions of Bloch waves, and these are our wave packets, and the wave packet is now called the Wannier function. And there is a mathematical procedure how you should pick the phases here to get the maximum normalization, but the simple picture is those Wannier functions are very, very close to the Gaussian ground state solution of the harmonic oscillator at each side. The wings are different, but I don't want to go into that. It is you transform from an orthonormal basis of Bloch wave function to another orthonormal basis of Wannier function, and the Wannier functions are as well localized as possible. That's the procedure. And now we can simply rewrite our total Hamiltonian or everything we are interested in, not in Bloch wave functions, but in Wannier wave functions. And what comes out now is that the bandwidth J is nothing else than our Hamiltonian with kinetic energy and the periodic potential. But J becomes now a matrix element between two Wannier functions. But the Wannier functions have now, I put in some indices in a moment, connect now two different sides. So it is, you have one Wannier function, you have the Hamiltonian, and connected to another Wannier function. So it is the amplitude that with the Hamiltonian, the particle can hop from one side to another side. So therefore, J, which was the bandwidth, is now the tunneling energy, or if divided by h bar, the tunneling rate from one side to the other side. For very deep lattice, everything is analytic and it can easily be solved. And I mentioned already in the tight binding approximation, you should think about your Wannier function as just localized Gaussian eigensolutions of the harmonic oscillator. Yes?
So sort of qualitatively, this question sounds sort of silly, but like normally when we write down this solution for J, like we're only considering like nearest neighbor hopping, but sort of from the math, I don't immediately see why we wouldn't include I equal to J.
Give me one more slide. So I should have actually. No, what I should have done is that J has an index here. I just didn't want to overload it with indices. I will immediately, I mean, this is sort of just telling you what J is in its simplest form. It is loaded with indices, and I will show you in a moment where those indices come in. So I just wanted to give you the idea that we want to have Wannier function. We hop from one Wannier function to the other one, and the operator is the Hamiltonian. And therefore, there should be an index, J and L, and maybe let me just do the next step first and then come back to it, but I wanted to tell you here what I'm aiming at, namely interpretation of J of tunneling from one side to the next. But right now I haven't really told you which J I really mean. There should be, based on the right-hand side, there is a J which has two indices. And I will make the indices disappear in a moment. But before I make those indices disappear, let me introduce the other relevant parameter, which will also have indices, and that is we have to bring in the interactions. We want to describe an interacting system. We describe an interacting system using the short-range approximation by assuming that two particles interact with a delta function. And if we have two particles on site, each of them has a density which is the Wannier function squared, and the product of the two densities integrated gives us the expectation value for the repulsive energy, and this is given here. So the moment we introduce interactions, we are now interested in the interaction energy between two particles, which in this case occupy the same site. Okay, so I've tried to introduce what sort of J is. J is a matrix element between two Wannier functions with the Hamiltonian in between. And U is the matrix element of two Wannier functions with the interaction operator in between. And now I want to use that concept to take my full Hamiltonian and transform from field operators localized at X to Wannier functions. So the B operator are now creation operators. They create an atom in a Wannier function. In other words, B dagger means you have a particle in a Wannier function at site I. And I just use that as a basis transformation, and the exact transformation of this Hamiltonian is now into this form. So what I have right now is I have the tunneling matrix element between particles at site I and J, and I have to sum over all of them. And in terms of interaction, I can take calculate this matrix element by using Wannier function with 4 different indices and ask what happens. And this is simply an exact way of rewriting it. And here I've given you the definition. So if you want, Matt, forget everything I told you about J and U. I've done a transformation, an exact transformation from field operators to Wannier function creation operators. And this introduces tunneling terms like this from site I to site J. And this here includes products of 4 Wannier functions which are responsible for the interaction term. Actually, if this is not complicated enough, I've suppressed band indices here. I should also now sum over all possible bands. But okay, I want to come now to the leading approximation in a tight binding model, and that is where, those Wannier functions are overlap. Two neighboring Wannier functions barely overlap. If I go further away, the overlap becomes even smaller. So the most dominant term are nearest neighbor interactions. And the nearest neighbor interaction is where I and J differ by 1. And this is what I call J without indices. And similarly, when it comes to the interaction term, where we have products of 4 Wannier functions, well, and we want to get the overlap of all 4, and then multiply it with G, the prefactor of our delta function, to get an interaction term. Well, the best overlap is if all indices are the same. And this is what I call U. So in that limit, in that tight binding limit, my Hamiltonian is now very simple. It consists of a tunneling term parameterized with J and an on-site interaction term parameterized with U. Yes?
So when we are saying I, J, and K and L are all same, so the interaction is with the particle itself?
No, 2 particles per site. When the 4 particles are the same, it turns into this Hamiltonian here has all indices are the same. And if you calculate that, it turns into product of two, BB dagger is the occupation number at each side. But if you are careful with commutators, it becomes occupation number times occupation number minus 1. If you have only one particle per side, this term is 0. So technically, U is, if you put in 2 times 1, if you have 2 particles per side, U is the interaction energy between 2 particles. Just use this expression to figure out what it is for 3 or 4, but for 1 particle you get 0. The self-interaction of a particle is absolutely 0. One particle does not interact with itself.
So, I guess back to my question with the hopping. So when you have I equals I, or I equals J for the hopping term,
yes?
do you just...
No, I assume, no, ij is nearest neighbor. I assume that the index I and j differ by 1.
Oh, yeah, I mean, so your argument was that the best overlap is between nearest neighbors?
Yes.
But, so, I mean, an overlap of the one-year functions with, like, at the same site is sort of the kinetic energy term, like, is it approximately 0, or do you just absorb that into the chemical potential?
This is 0.
The lowest band is a 0 point energy. It's the common.
Wait, p square, it's...
So we're only looking at nearest neighbors, so we essentially saying the case where I equals j is approximately 0, you say it's just common.
Yeah, because it's the matrix element of the Hamiltonian. So
Yeah.
P, the kinetic plus the lattice operator. So if I take my one-year function, which is built out of eigenvalues of that equation, you get a sum over a bunch of energy terms. On every site, those are the same. So you have a common mode energy that you can just emit.
Well, then it's multiplied by the B dagger B.
Yeah.
So like in some sense it would have to be absorbed into the chemical potential.
My gut feeling is, and this is why nobody considers it, it's just the constant energy, which is probably something like the 0-point energy times the number of particles, which is not affecting any dynamics. It's pretty much a constant which can be simply dropped. Let me just go back to that slide, I hope. Let me just look up the reference. I haven't looked at it recently. When we do this exact transformation, there should be a reference whether I and j are what happens when I equals j. I think it's just a constant term.
Yeah, it must be. Because then you're summing over every single lattice site. So you get the number of particles times 0-point energy.
Yeah, but even mathematically, it gives just a constant term here, which is neglected. No, thanks. It was good to clarify it. Okay, I think within the next 20 minutes, I can step you through the superfluid to mode insulator transition. First, references for what I've just said are given here. But let me now take this Bose-Hubbard model and discuss its 2 limiting cases. One case is where U is much larger than J. The other case is where J is much larger than U. These are the 2 limiting cases. And it will turn out that one is an insulator and one is a superfluid. I mean, that makes perfect sense, of course. If U is much larger than J, I can set J equals to 0 if I can neglect it. No tunneling means no transport, and that means an insulator. It's also clear that when there is no tunneling, that the system is really described by a product of so and so many particles per site. So it could be 1 particle per site, and I have a product of over all sites, or 2 particles per site. So this will be the ground state, and it's called the ground state of the mod insulator. It's also trivial to discuss what happens if J is much, much larger than U, because then I simply neglect U, and I have a free gas, well, a free gas of Bloch wave function, but that's the same as a free gas of planar wave function. It's just that quasi-momentum replaces momentum. And if you have just an ideal Bose gas in a periodic lattice, instead of Bose-Einstein condensation in the lowest momentum state, you have Bose-Einstein condensation in the lowest quasi-momentum state. The lowest quasi-momentum state is a superposition of all Wannier function. I mean, the zero momentum state in free space is a superposition of all delta functions, of all position delta functions. The plane wave is delocalized, and the lowest quasi-momentum state is just completely delocalized over all Wannier functions. But this is nothing else than the Q equals 0 quasi-momentum Bloch wave. The interesting question is, and this has led to hundreds, if not more, papers in the literature, how do we go from one limit to the other limit? And now you would say, well, maybe we should use what has worked so well. We should use the Bogolyubov approximation, just assume we have a condensate, replace all those kind of A0 operators for the lowest Bloch waves. However, this doesn't work, because the interesting thing here is to find the transition from the superfluid, from the Bose-Einstein condensate to an insulating state. The nature of this approximation is that you need n0 to be large, but we are interested when the condensate wave function turns to 0, and in the insulator it becomes 0. So we are actually interested in the opposite limit. And indeed, if you would ignore everything I've just said, that it doesn't make sense to make this approximation, you make it nevertheless, you will find that you never get the insulating state, because you've pretty much eliminated the possibility to describe an insulating state by doing this approximation. So I want to show you now that we have to do another mean field approximation, which is actually nice. It's very different from this Bogolyubov's approximation, but it's also mean field approximation which will describe our system. So the goal is now that I want to find an effective Hamiltonian which describes the transition from here to there. And the important approximation I will use is the following. Again, I have to get rid of operators. Products of too many operators cannot be solved. And so what I will do is I will use products of operators, write them as average value plus fluctuations. And then when I multiply that out, I take the product of the average values, and I include the fluctuations in leading order. So I take delta A times B and delta B times A average, but I neglect the product of those fluctuations. You can say I neglect the correlation of fluctuations here. So this is spelled out here, but since I want you, the sign is important, just look at this equation, A delta B plus delta B with B plus A average times B average. If I absorb A times B by upgrading delta B to B, but I do the same here, I have to subtract one product of the two average values. It's actually this minus sign which will play a role later, but here you see already that I will make this decoupling approximation, that I decouple the fluctuations from each other, and I write it in this way. There is an important minus sign. Okay, so we want to start in the insulating state and want to figure out how does the system develop superfluidity out of the insulating state. And the perturbation operator which takes me out of the insulating state is tunneling. So therefore, the operator which is responsible of breaking out of the insulating state is the operator which induces tunneling between neighboring sites. And the tunneling operator in this Hamiltonian, remember the Bose-Hubbard model had J times B dagger B. This was our tunneling term. This involves now products of operators. And I told you, we want to get rid of products of operators to get something we can easily solve. So we use now this product of operators on two neighboring sites, and we use exactly this decoupling approximation. So therefore, we replace each operator by an average value, and we neglect the product of the fluctuations, and then we obtain this, and I've explained to you where the minus sign came from. So now I call this average value of the operator BL, I call the superfluid order parameter psi. I think I could have chosen psi to be complex, and then BL, dagger BL would have complex conjugate, but it is sufficient here to restrict the discussion on real numbers, and it makes the notation simpler. So anyway, so I introduce that, and what happens now is the following, that I have my Hamiltonian. The Hamiltonian had the interaction energy, but the tunneling term is now very simplified, because instead of tunneling from one side to a neighboring side, the other side is sort of absorbed by the mean field, by the superfluid order parameter psi. And therefore, and this here gives me a psi square term which appears here. Trust me, this is just an identical rewrite of the previous Hamiltonian by using this decoupling approximation. So well, what we have gained now is something really dramatic. We had sort of many sides and tunneling from side to side, but if you look at it now, we simply multiply the effective Hamiltonian, we sum the effective Hamiltonian over side index L. So our effective Hamiltonian is now the sum of an identical Hamiltonian per side. The sides no longer interact with each other. Each side interacts with all the other sides described by the mean field by the superfluid order parameter psi. So therefore, our many-body problem, which is still a many-body problem, but has turned into an effective Hamiltonian for each side, because each side has the same Hamiltonian. Colin?
What happened to the J psi squared term?
This here?
Oh, okay, yeah, sorry.
Okay, so here is now, so I can say instead of solving for the sum, I can just solve for each side individually. And this is now my effective Hamiltonian for each side. Now, I want to catch the onset of superfluidity. So I want to get the system when psi is small. And therefore, I can just ask, I don't know what psi is. It's part of my solution. But I'm interested in the moment when psi begins to take off from zero, when superfluidity emerges. So what I can therefore do is, I can regard psi as an epsilon parameter, as a small parameter. And the psi parameter comes with an operator v, and this operator v is nothing else than BL dagger plus BL. So in other words, what I'm doing is I'm separating my Hamiltonian into a Hamiltonian which is diagonal in the quantum numbers of the isolating state, just 1, 2, 3 particles per side. And psi square is a C number. The psi square is also diagonal in that. And now the possibility of tunneling, the possibility of superfluidity is now perturbative in this term psi times v. Okay, I don't want to explain actually this expression. It just formalizes, I need it as an intermediate step. When we have the chemical potential and we raise the chemical potential, we go from 0 to 1 particles per side to 2 particles per side. And whatever the chemical potential is determines whether we have 1 or 2 particles per side. This is just telling me, as a function of chemical potential, what is the ground state of the insulator. So now we take this ground state, it's actually much easier described in words than by this formula. We take this ground state and do perturbation theory in our term psi times v. Remember, the operator is b dagger b, and the epsilon is psi. So in second order perturbation theory, we get psi square. And then V, because it's BB dagger, is very simple. It only couples one side to the next. It couples one occupation number n to n plus 1 and n minus 1, because B and B dagger destroy or create a particle per side. So therefore, I can immediately write down what this matrix element is in second-order perturbation theory. I mean, these are all, sorry, it's all defined here. I know I'm losing you now. Nobody will tell me what is the difference between U bar and U, but it's trivially defined. So the idea is we have the isolating system, we do perturbation theory in tunneling, and the perturbative operator is psi times B plus B dagger. The B plus B dagger matrix elements are trivial because they admix to n particles per side, n plus 1 and n minus 1. And this is what we've done here.
And the J's are just occupation numbers?
The J is the occupation number of our site.
I guess two questions. So in the bottom equation, what happens to the psi squared?
Sorry, this is the sum. The psi square is missing.
I guess it's the same for the same question for the equation next to the green thing. Is there supposed to be a psi squared in there? Because originally there's a psi squared in the H dot.
No, this is the ground state where psi is 0, and now we do perturbation theory in psi v. So we pretty much use, these are the unperturbed energies which appear in the energy denominator. The wave functions we are using are Fock states, number states per site, and here we couple occupation number j to all possible n's. But because of B and B dagger, n has only two values, j plus 1 and j minus 1, and this is what's given here. It's mathematically trivial. The notation is more complicated than the physics behind it. But now comes again, I think I need 5 more minutes and I'm done. But now comes the interesting physics. We have to ask, what are we doing here? I mean, it's all mathematical, and the math is really simple here. What we have done is we have looked at the isolating state, and we have done perturbation theory in psi times B plus B dagger. And now we get an energy correction, which is psi square. And I mean, what are we really doing here? Well, you can say the following. We started with the hypothesis that we have a superfluid state characterized by psi, and psi at the onset of superfluidity is small. But now we have done the calculation assuming that there is a psi, but now we are turning around and said, have we really done the system a favor by introducing superfluidity? In other words, has our perturbation theory in psi lowered the energy of the state or raised the energy of the state? So in other words, we've done a hypothetical calculation. Hey, what would the system feel like if there were a little bit of superfluidity? If the system says, great, I've lowered my energy, then we know we are in the superfluid state. When the system says, no, I raise my energy because of the psi, then the system has rejected our idea to introduce superfluidity. So therefore, the question we are raising now is, after we've done the calculation, for what values of u and j is it favorable to introduce a psi or not? Now, I was expecting the question of some of you that in second-order perturbation theory always lowers the energy. But remember, this is why I emphasized the minus sign. We had a psi square term which came from the last term of the decoupling approximation, which had a minus sign. And therefore, we have in psi square one term which came from this special sign I emphasized in the decoupling approximation, and we have a contribution of psi square which comes from perturbation theory. And the two together can actually change their sign. So what we have right now is, if we describe the ground state as a function of psi, we have our unperturbed energy of the mod insulating states, and then we have a term in psi square. And we should, and we could, but we don't, calculate the next order in psi to the 4. And it turns out that in fourth order perturbation theory, this term is always positive. So what happens now to the total energy when this term A2, which we have exactly calculated, analytically calculated if this term A2 is larger or smaller than 0. Well, if you have a parabolic term and a quadratic term, in this case, both the quadratic and the quadratic term are opening up like in a U shape, but here the total energy turns into W shape. And the interpretation is fairly simple. Under those conditions, the system prefers to have psi equals 0, whereas here it's like the system wants to have a psi parameter which is finite, either positive or negative, and whether it's positive or negative is sometimes called spontaneous symmetry breaking between two degenerate solutions. What I'm showing here is, of course, very similar to the Ginzburg-Landau theory of phase transitions, where you have an effective potential, and the phase transition takes place when the second-order coefficient changes sign, and the effective potential turns from U shape into W shape. So that's what we have done. So anyway, I think this is a nice problem where the interpretation is, I think, much more subtle than the calculation itself, but we have calculated the phase transition. Everything is analytic. Here is the analytic result, which I know with very indigestible notation. The paper, I followed exactly the paper by Van der Straten, Stoff, and collaborators, which is posted on the website. You can plot this phase diagram in this way, but if you use what is more common, normalize the chemical potential by U and normalize J by U, you get these wonderful lobes of the mod insulator, where you see that if you increase the chemical potential, you have n equals 1, n equals 2, n equals 3 mod insulator, and in between you go through superfluid regions. However, if your tunneling is larger, if your tunneling is too large, you're only superfluid. So this is sort of the way how you derive this rather rich phase diagram of bosonic atoms in an optical lattice. Green is an insulating state, and white is the superfluid state. Let me just conclude by showing a few slides how this can be observed. So in one case, we have an insulating state with a definite number of particles per side, and here we have superfluid state, which has the normal fluctuations in number. Here's another cartoon picture of a condensate in the lowest Bloch wave function, and here you have localized number states. Often you observe the transition by taking the system and releasing it in time of flight into ballistic expansion. If the superfluid is coherent, the wave function on the different sides is coherent, and what you get is a multi-slit interference pattern, which is a diffraction pattern, and you see these characteristic diffraction patterns. It's an n-slit diffraction pattern which characterizes the coherence in the initial state. However, if you have a completely isolating state, you have a Gaussian wave packet on each side, which has nothing to do with the next neighbor, and then the Gaussian wave function simply expands in a structureless way. And so the transition from here to there happens exactly when the ratio of U over J crosses the value we have derived. There is another technique of observing that which is more recent. This is quantum gas microscopes, where you do the same physics in 2 dimensions, so you have only one plane where this physics takes place. And you can observe atoms now with a microscope. So each green dot here is an atom. You can sort of zoom in, and if you now study the region where you go through the superfluid to the mod insulator, you see that you have exactly 1 atom per side. If you increase the atom number, you have an insulator with 1 atom per side, and in the middle you have an atom, you have a state with 2 atoms per side, which for reasons I don't want to discuss are color-coded here in black. And that sort of goes on and goes on. So you can really resolve side per side the occupation of the number of atoms per side. So I think I stop here with the Bose gases. When you think the mod insulator is the end of the story, all motion has been frozen out and you have one particle per side, well, it could be the beginning of a new story, because if we use two different hyperfine states, spin up and spin down, we can talk about spin ordering, but this would be a whole different lecture.